Hi, my name is Will Wolfe, and today we're going to talk about constraints on radon and SGD temporal variability in a semi-arid, well-mixed estuary. This project has had some support from the Texas General Land Office, Sea Grant Texas, Center for Coastal Studies, and of course the kind folks at the Center for Water Supply Studies at Texas A&M University, Corpus Christi. The goal of this study is to investigate the temporal variability of Radon222 in an often turbulent, shallow estuary through continuous high-resolution measurements. And by correlating radon to atmospheric and hydrologic conditions, we hope to improve on estimations of submarine groundwater discharge to the region. So to give a quick outline of what we're going to talk about, we'll start off with background, just defining SGD and its broader impacts, and also how we trace it using Radon222. And then I'll go into our study site and the data collection, as well as the types of modeling that were used to explain radon here. And then the results are going to include model performance, model interpretation, and then finally quantifying SGD using these model results. Submarine groundwater discharge, abbreviated SGD, is defined as any and all flow of water from the seabed to the coastal ocean. And it's primarily driven by water table gradient, elevation differences between groundwater and surface water. It's really diffuse, it's heterogeneous, it's really difficult to measure, especially in these sandy coastlines. And there's other factors affecting it, such as wave action, tidal pumping, seasonal oscillations. Although often overlooked when considering coastal water budgets, this process can provide significant amounts of water inputs, especially in arid regions where surface water inflows are scarce. It also carries with it a variety of land-derived nutrients and pollutants, with several studies linking submarine groundwater discharge to harmful algal blooms and decreased water quality. One of the methods available for tracing submarine groundwater discharge is Radon222. This is a naturally occurring product of uranium-238 decay. It occurs in sediments, especially in the coastal bend of Texas. It enters the surface water through groundwater advection and sometimes diffusion. We use it a lot for estimating basin-wide SGD fluxes. There's some pros and cons to it. First of all, on the pro side, it's a conservative noble gas, so it doesn't react with anything. It's a very short half-life, representing very young groundwater, so it dissipates through decay very quickly. It's also dominantly terrestrial, and so it's enriched in groundwater compared to surface water, up to sometimes, to 1,000,000 times more than surface water. It outgasses really quickly, though, so this makes it difficult. It's in a windy, shallow environment especially, it will dissipate to the atmosphere rather quickly, within the matter of hours. It also mixes with offshore waters. It's spatially and temporally variable in groundwater and surface water, so finding the end member, finding the source concentration can be really difficult. To estimate groundwater flow rate using Radon222, we use a non-steady state mass balance. In brief, we measure the change in radon over time and compare that to the source or end member activity. The first step is to convert radon activity to radon inventory by multiplying it by the water depth at the point of collection. This is essentially normalizing it to the tide height of the changing water column. Next, we attempt to compensate for any gains or losses that have occurred, including atmospheric evasion, mixing with offshore waters, and production by the parent isotope. Then we integrate over the time between measurements before dividing by the end member activity, which finally gives us a flow rate. This method makes many assumptions, but provides a unique basin-wide estimate that other approaches lack. So here's an overview of how this study was carried out. It began in September of 2019 with data collection. That's surface water, Radon222, end member Radon222, environmental parameters, and then processing the data to get everything onto 30-minute time steps, as well as converting wind, direction, and vector, and adding lag times, manipulating variables to get a really thorough data set. And then creating models for radon inventory, since radon inventory is kind of our most important factor in the mass balance. We use a multilinear regression and a random forest model to predict and explain radon. I've validated the best model and use that to predict on the entire data set, and then do a little bit of interpretation of each model, and finally go into mass balance computation of SGD using both the observed and the predicted radon inventory. This study was carried out on Ward Island in Corpus Christi Bay. This is in the southern part of Texas Gulf Coast. This is also the campus of Texas A&M University, Corpus Christi. On this beach in front of the campus, we have a platform that contains a Rad7 and a Rad Aqua system that measures Radon222 continuously and autonomously at 30-minute intervals. And so I've combined this data with atmospheric and hydrologic parameters from the USGS, NOAA, and the USAF stations that were within 10 kilometers of the study site. Water intake at this spot was about 1 meter depth, and I was able to get continuous atmospheric and hydrologic parameters to combine with semi-continuous periodic measurements of Radon222. This figure summarizes the data that has been collected up till now for this study. Atmospheric and hydro parameters are continuous on 30-minute intervals and include wind speed and direction, water and air temperature, tide height, and surface water inflow from a nearby creek at a USGS gauge. So radon is less continuous and shows several gaps. The largest gap begins on July 27th of 2020 when Hurricane Hannah made landfall and destroyed the research platform. You can see the storm surge and the wind speed spike at that time. Also visible in February of 2021 is the big freeze that we experienced. The seasonal temperature oscillation is also pronounced in green, which turns out to be a significant factor in the models. A major component of this study is the wind direction. Since the movement of water masses in our area is primarily governed by the wind rose on the left summarizes the dominant wind speed and direction for this study period, commonly out of the southeast at 4 to 8 meters per second. So instead of using radial wind direction in degrees from north, this study was decomposed into the trigonometric components along 6 axes. So for instance, wind from directly north would be represented by 1 and directly south, -1. This process is repeated for east, west, and the 4 other intermediate directions to allow for any particular wind direction to stand out against the others in a numerical model. So next in the variable manipulation is going to be lagging wind direction. So since not all of these relationships are immediate, we're going to look back through time steps at 30-minute intervals and look for correlation coefficients between radon inventory and the wind direction at that time. The first one is north-south, as shown here, and we do this for all 6 other axes, and we can see peaks and valleys here showing a positive or negative correlation with wind direction and radon inventory. So each of these peaks or valleys is highlighted and selected, and a new variable is made by shifting data to these significant lag peaks. So we've really built up the number of variables that are adding to this model. So the last step in data processing is to finish creating these wind vectors by actually multiplying them by wind speed and wind speed squared to pick up any nonlinear relationships between wind speed and radon inventory. We're also looking at lags between the Oso Creek discharge and radon inventory, as well as air and water temperature. So anything that had a significant peak or valley in its lag plot was created as a new variable. And here's a summary of everything that's going into these first few models. On the left column are the actual measured values of inventory and the variables that we have. And then these manipulated variables, these created variables using log or lagging or squaring or trig vector. So we end up with over 32,000 of these initial input variables. So there's 57 input variables, and they total over 32,000. And then radon inventory is a little over 10,000. So next we're going to go on to the modeling and show some of these initial results. These 2 plots show the results of the multilinear regression and random forest models. I've plotted the observed radon inventory on the x-axis and the predicted on the y, with the dotted red line representing 1:1. Both models underwent a certain degree of curation by removing any of the original 57 variables through backward stepwise regression. The models were run with every variable included at first, then one by one the least significant variable was removed and the process repeated until everything had reached the threshold, and each made a highly significant contribution to the prediction. For the multilinear regression, this threshold was a p-value of under 1 × 10 to the -5th. And since the random forest doesn't use p-values but rather node purity, which represents the value importance, I chose greater than 2 million as the cutoff for this model. The random forest clearly outperforms the multilinear regression, likely due to the fact that many of the relationships in this system are nonlinear, and random forest regression is well suited to account for nonlinearity. So before throwing out the multilinear regression model, We'll look first at the summary table. So this shows the coefficients of every variable in this linear model to explain radon as a function of all of these 23 variables that remained highly significant. So by highlighting just the ones with almost a zero p-value, extremely significant variables, we can see that wind speed direction vectors kind of dominate the scene, and Oso Creek discharge and water temperature also have a strong effect. So beyond this, though, since the results or the performance of this model were so poor, there's not much we can take from this other than the fact that we know we've eliminated some of the variables, and we will compare these to what we see in the random forest model. So the random forest summary is in the form of a variable importance chart. This ranks each of the variables depending on how much of an impact they had in determining the ultimate mean value of radon inventory that was predicted. So working down the list here, water temperature is much higher than anything else, likely due just because it's a seasonal oscillating variable, and we have a lot of seasonal effects on radon inventory. Water temperature may not be directly affecting radon inventory, but it's correlated with it in a way that it picks up in this model very nicely. So the lagged wind speed of 9 hours is also the second most important variable in this model, followed by the north, northeast, and south, southwest wind speed vector. And that conveniently is also the longshore, directly offshore and onshore wind direction for this study area. The Oso Creek and the tide and the air temperature also fit in there, and a variety of almost all the wind speed lag and wind speed vectors are out of the north, northeast, and south, southwest. And as an aside, to follow up on the wind vector importance, this figure kind of shows this offshore and onshore orientation of the north, northeast direction and the south, southwest. So anything coming from the south-southwest direction is coming from Oso Bay. This is a more terrestrial source, likely to include a lot more radon. Corpus Christi Bay has much more communication with the Gulf of Mexico, should be radon depleted because it's a marine source. And the platform is situated right here next to this channel, within about a mile of this channel, which is a major point for water exchange between these two water masses. If we're going to use the random forest model to predict during the gap periods, we will need to see how it behaves out of its comfort zone, so to speak. To do this, I trained a model using only 50% of the inventory data, then used that model to predict inventory on the remaining half, and tested it against that remaining half. Both the training and testing models show good performance with an R-squared around 0.83. This suggests that the full model using all of the data will be likely to give us an accurate prediction over the gap periods. Here we see just the measured data, covering about 1/3 of the study period. Although most of the spikes appear to occur in the summer, there really is no clear seasonal trend. But since the input variables used to build this model have no gaps and are readily available, we can go back in time and predict radon with a reasonable degree of confidence during those times when the platform was not operating. Now, with the model predictions, an annual cycle is much more apparent. The biggest spikes in radon inventory appear in the warmest months of late spring, summer, and early fall. Although certainly related to enhanced SGD fluxes, larger radon inventories seen here are more likely due to radon accumulation during periods of calm winds and favorable currents and tides. Nevertheless, this model allows us more accurate understanding of the forces acting on radon, which is an important step towards constraining actual groundwater discharge rates. So if we zoom in just around a few months in 2020, we can just see how quickly radon builds up and dissipates. And we go back and look one more time even closer, around a few weeks, we can see how complicated this pattern is when you're measuring over small scales. So I mentioned earlier about the mass balance method for converting radon inventory to groundwater seepage velocity. To briefly recap, the inventory values are compensated for losses to the atmosphere in mixing with offshore waters, subtracted for parent isotope production, integrated for changes over time, and divided by source concentration to finally arrive at a seepage rate. Here, the estimated SGD rates show an even more distinct seasonal pattern of highest in the summer, lowest in the winter. However, the resemblance of this plot to that of the radon inventory is strikingly similar. Knowing that this model of basic environmental conditions can so accurately explain radon inventory, this similarity suggests that parts of the mass balance equation we are using do not account for all sources in sink of radon as it emerges from the sediments and moves through the water column. So future work is being carried out to identify these major sources of uncertainty that are inherent to this mass balance equation, and I hope to report on them soon. And that's going to do it for me. Thanks for tuning in, and please get in touch with me if you have any questions.